Hi, everyone. This week, we're very happy to have Josh. And Josh did not send an abstract, so I have no idea what he's going to talk about. So take it away, Josh.
That's for the best. Who knows if you would have came if I had.
That means the after.
What is that diagram?
Well, you will learn during the talks.
Is this pandemic?
Yeah, I'm gonna talk about some that. Thank you. This is my first time here for a while. I think since I was a postdoc myself, and then this new building is amazing, and I'm jealous of it. Okay. So I'm gonna talk about dark sector stuff. Sorry. Okay, and the talk will really be two disconnected parts, maybe 2/3 one thing, 1/3 another thing. And then this slide and the title is how I kind of tie it together artificially. My inner voice is my own. So yeah, the common theme will be things out of equilibrium are going to be very important. So I just wanted to spend one slide and celebrate equilibrium before leaving it. So equilibrium is great. And a lot of models of dark matter assume equilibrium. So why is it great? Well, we know the phase space, and then things that depart from equilibrium can have a different phase space and actually can be very complex when you depart. Yeah, like we have spectacularly confirmed the phase space of the CMB. And equilibrium is insensitive to initial conditions like this. For thermal relics, this is a key fact. And this is great. It's celebrated. It's why they're predictive. Although the bad thing is you lose information about what happens early on because equilibrium washes out information about the initial condition. So that's kind of the bad aspects, but the good and bad. It's predictive because everything happens in the infrared, but it removes sensitivity to what's there before. Okay, so equilibrium is great. And then this talk will be about some dark sector phenomenology where departures from equilibrium are critical. Okay, but really it's two different topics where that's a common theme. So in the beginning, I'll tell you about a new weird idea for making dark matter using exponential growth. And then in the second part, I'll talk about some results involving oscillations between photons and dark photons. For both of these will be non-equilibrium topics. Okay, that's the plan. And this will be kind of disconnected, like I said. So, and this will be most of the time, I think. Okay, so first, exponentially growing dark matter. So we had the idea that dark matter could have been produced through a period of exponential growth. So I'll describe this idea in general, and then I'll describe its application to sterile neutrinos, which is, I think, a nice application of it. Okay, yeah, so we wrote two papers about this. The first is the general idea, and then the second is this application to sterile neutrinos. Okay, so before I do that, I'll just do one slide of review on ways you already know about how to make dark matter to serve as a point of comparison to this exponential growth. So this is totally a review for all the experts here. So thermal relic, Witt miracle is great. Yeah, like people might have in mind annihilations into standard model particles through weak interactions, but of course it's a much more general idea. The dark matter, if it annihilates to a state and if it's in equilibrium, then the number density is given by the solution to this Boltzmann equation. It starts in equilibrium, and then when the annihilation rate is slower than Hubble, you freeze out. And then the relative density, the energy density, just depends on the cross section. It goes like 1 over cross section, because larger cross section stays in equilibrium longer, smaller cross section departs sooner. So you get this 1 over cross section, and then the amount of dark matter is predicted by the cross section. So that's great. Okay. A second kind of opposite idea is freezing. And here the idea is you start out of equilibrium, and you have small couplings. So sort of thermal relic is big couplings, freezing is small couplings. And normally it's assumed you start with 0 dark matter as initial condition. That's a choice, but that's the choice. Normally the assumption people make. And then the rates are not big enough to bring it into equilibrium, but you still can slowly leak it in and build up to the observed amount. So in this example, assuming some state in equilibrium is annihilating the dark matter. You can consider other processes like decay. But anyway, then you solve this Boltzmann equation. Yeah, technically the difference between these two is here you neglect the inverse process because that's negligible. So that's why it's only one term here. Anyway, if you assume you start at 0, you kind of leak it in. Your production tends to be dominated by temperature on the order of the sort of heaviest mass particle that's relevant for this. So sort of infrared dominated at the mass threshold, and then it's sort of negligible leaking at later times relative to the amount you made at that threshold. So that would be like this spot there. So it's like kind of the opposite from freeze out, and that you start small initially instead of starting big and build it up, and then the relic density in this case is proportional to the rate that makes it like the cross section. So it's the opposite dependence. Here you have 1 over cross section, here you have a cross section in the numerator.
So in the case of freeze out, there is this famous wind miracle prediction, right? So
Yeah,
if you take weak scale cross sections and weak scale masses, what do you get for omega?
Yeah,
You get the inverse,
yeah.
or
and the Witt miracle is really that the cross section should be this
Sure.
1 over T quality M Planck, and then that accidentally is near the weak scale. So here I showed the dependence is a bit different. It's not any analogous miracle.
miracle? Yeah.
But like if I remember correctly, for like a GeV or 10 GeV-ish particle, you typically want couplings like 10 to the minus 8. I don't know. Any
I see.
experts
So is the
remember a different number here.
That's about -10 is the benchmark.
So depends a lot on what size of the coupling is what you will get eventually.
Indeed, but you don't get this nice. I'm not aware of any analogous statement to the Witt miracle, which itself is very interesting, but maybe an X these parameters. Very, very cool. Yeah. Okay.
You can only be wonder.
Yeah. Surely.
No, you read the Bible and there's so many different ones, from converting water in wine to working on water. So
Since this is on Zoom, I'm not going to give you my.
What are you talking about?
I have a whole routine that I'm not going to give now.
Yeah.
But if we turned it off. Okay. I want to specifically emphasize how these two freeze out and freeze in paradigms depend on initial condition, because that'll be very different for the mechanism I'm going to introduce. So for freeze out, you start in equilibrium, and like I showed you before, that's great, and it's sort of an attractor. Technically, if you have some process at high temperatures that adds or removes dark matter, it rethermalizes and you lose sensitivity to that process. So in that sense, it's an attractor, and then you remove information from beforehand. Okay. On the other hand, for freeze-in, the initial condition is important. Actually, people normally assume initial condition of 0, but more precisely, if you assume that you have a small enough number that you're far below the equilibrium number density, then the initial condition enters additively. So there's some amount produced by freeze-in. You should add that to whatever amount is present initially, and there could be some from whatever inflaton decay, some other non-thermal mechanism, then evaporation of black holes, whatever you want, and you would add that to this. So the initial condition, people normally don't say that. They normally, when they're studying freeze-in, start at 0, but more precisely, the initial condition is additive. Yeah, and then that means the amount you make from freeze-in is insensitive to the amount of dark matter that was there beforehand. And the reason for that is that the inverse process is small. Okay. So now I'll talk about a third thing, which will visually look like that. Which is exponential growth of some initial amount. Okay. So yeah, here this will be similar to freeze-in in that I'm going to assume that I'm in a small coupling regime where the dark matter begins with a small number density relative to the equilibrium number density, and then I'm going to assume that some process is present where it can scatter against states that are themselves in equilibrium, so that you can have one dark matter that makes two dark matter. Yeah, and then you would the number density is given by the solution to this Boltzmann equation. Yeah, where it depends now on on both of these number densities. It's kind of the key difference from freezing. If I go back, freezing does, the rate didn't depend on the initial amount of dark matter. There's no dependence on the amount of dark matter. Okay. Yeah. So if you have one that can go to 2 and then 2 to 4, this gives exponential growth. Oh, yeah. Sorry.
And why you always need to assume psi equilibrium?
You don't. Yeah, we just chose to. Yeah, so that just analogously to freezing, you could ask the same question. Yeah, so we chose that as a simplifying assumption. That will hold for the example I'll show later with neutrinos, but it would be interesting to consider deformations from that. We just haven't yet. Yeah, so you could certainly generalize this to have this stay non-equilibrium. I agree. Yeah, so for this talk, I'm going to assume that it's in equilibrium.
Or psi is some other thing.
Yeah,
It's not
not dark matter, and
not standard model and some.
well, it could be standard model or not standard model. I'll actually give examples of both types in this talk.
So
So
you don't have like a vertices like 3 psi 1 chi or something. You only have a 1 psi 3 chi.
yeah, or at least this is, I'm assuming this is dominating for the chi production. Yeah, but yeah, you could consider other vertices absolutely. Yeah, so if you had a 3 psi and 1 chi, that wouldn't that could freeze in some amount of chi. That would be ordinary freedom in that case. So here I'm assuming this is dominating over traditional freezing.
And the chi is
like that.
stable because there's nothing else.
Yeah, well, if chi, I haven't said the mass ordering, you can actually consider either ordering here. If chi is lighter than psi, yeah, then they could be both, for example, driven under Z2, yeah, and then chi can be stable. If chi is heavier than psi, then chi is unstable to decay to psi. And that's fine too, then it has to be long enough lived. So you can consider either ordering, but chi needs to be lighter for the exact stable.
So if the goal is eventually to build up an abundance of chi that's greater than equilibrium, wouldn't you worry about the reverse process?
Yeah, I'm not, my goal is not gonna be to reach equilibrium, but indeed, if it did thermalize, then the reverse process would be important. I'm gonna consider cases where it doesn't reach equilibrium.
But yeah, even independently of the question of whether it reaches equilibrium, if you just have a whole bunch of chi's lying around, I would imagine that you wouldn't be in a regime, equilibrium or not, where annihilation of chi to chi psi would be important. No, you're saying that you never find that regime?
Yeah, I'm not gonna be in that regime. Similarly to freezing, typically freezing doesn't enter that regime either.
Okay.
Yeah, you could consider that, but typically freezing models that reach the right abundance, because the right abundance is normally far below equilibrium abundance, the inverse decay is normally negligible, and that'll be true here too. Yeah, but yeah, exactly. So same comment would apply here, and for when you hit the right yield, then you're typically going to be way below equilibrium, and then that's why for freezing you can neglect the inverse decay to good approximation. Okay, great. Yeah, so the solution to this equation is just exponential growth. Yeah, here this is written in terms of yield, and then you exponentiate the number density of the equilibrium state times cross section, which is the rate of this per Hubble. So that's the thing that gets exponentiated, and then whatever. And you start with some amount, of course. If you have 0 initially, then this can't happen. But if you have some amount, then you exponentially grow that amount by this exponential growth factor.
Why do, stupid question, but why do you multiply divide by 3? So it's a convention or?
Yeah, it's gonna be to make connection to something I'll say later.
Okay.
That's gonna be mostly a joke, but partly realistic. Okay. But yeah, you don't have to. Okay. Yeah, so here you can see explicitly the initial condition enters multiplicatively. So that's very different than freezing where it's additive or thermal relic where it's just the equilibrium. So it's the third way that the final amount of dark matter can depend on the initial amount of dark matter. Yeah.
Do you assume that chi and psi are in equilibrium with each other, which means they have the same temperature?
No, so chi is out of equilibrium and psi is in equilibrium. Yeah, so chi doesn't have a temperature, it's out of equilibrium. Yeah, so I'm assuming that this coupling is small enough that it hasn't brought them into equilibrium. And then when the exponential growth is happening, you can think of it as it's like trying to enter equilibrium, but then you need to stop the growth to hit the observed dark matter abundance before it
Yeah,
reaches
because I think by using this form of the Boltzmann equation, actually people are implicitly assuming that the dark matter is in equilibrium with the background, so that they have the same temperature, and then you can integrate the phase space distribution on both sides, and then you get the number density.
Yeah, you're right.
Yeah.
Yeah, indeed. Well, you get so you're right. You should really think of, in general, you should think of a generic phase space distribution. So I'm oversimplifying. You're right. I'll consider an example later where chi will have other interactions, so that it will be in equilibrium with a different temperature, and then this will be exactly right. But you're right. If you consider a generic phase distribution, you actually still get this as the left-hand side. So, but then you have to like sort of define this object with care, where you need to integrate over the actual phase space distribution that's different from equilibrium. So this equation can still be meaningful for that case, but then you need to define this object with care, and you actually need to solve for the full phase space evolution. So I'm going to consider two example models later. Oh, the more interesting second one, actually it'll be in equilibrium with its own temperature. In the first one, we're going to simplify things actually, and assume something is similar to equilibrium that might not be true, and that would be interesting to study. So that's a good question. Very good. Okay. I'm going to consider the regime where you start far with a small abundance out of equilibrium, and then the exponential growth occurs in the infrared. So that doesn't work if you consider higher dimension operators generating this interaction, because it would be then UV dominated, and the exponential growth would have had to happen at reheating. So I'm going to consider the case where this interaction is generated from relevant or marginal operators, like not higher dimension operators, so some normalizable theory. And then this can enter equilibrium in the infrared, and just that. So this is the exponential growth object. And if we're at temperatures above these two masses, then this number density of psi would go like T cubed. Hubble goes like T squared over Planck. So this rate would go like temperature times this cross section, and this cross section would normally go like 1 over temperature squared. So this thing that gets exponentiated goes as 1 over temperature for as long as it's not higher dimension operators, then it would be some higher power of temperature. So it grows in importance in the infrared. It's the same argument for Friesen. So you can start with this unimportant, and then as your universe cools, you can reach an epoch where the figure exponentiating becomes order 1, and then the exponential growth will suddenly occur in the infrared. So that's the type of model I'm going to consider. Yeah, so this thing that gets exponentiated will grow like 1 over temperature, and then you'll hit some exponential growth moment.
And it will stop when you're running out of psi.
Yeah, good question. So if it doesn't stop, what happens is it would just thermalize. So I want to consider the case where thermalization is unsuccessful. So I need to consider the case where this stops. So that's going to be my next slide, I think. Yeah, so I'm going to here consider what stops it. And I'm going to have it stop by hitting a mass threshold. And then the parametrics depend on the mass ordering. So I'm going to consider on the slide both cases. So if chi is lighter than psi, then this number density will just go like, I'll have the Boltzmann suppression when it's non-relativistic. So then this R factor will become exponentially small when psi is non-relativistic, and that can shut off the exponential growth. Okay. For the other hierarchy, this process itself requires some temperature to occur, right? So it gets suppressed by this factor when you're non-relativistic. If chi is heavier, right, then you have to convert a psi into a chi, and that takes some energy that itself is Boltzmann suppressed. So then when you multiply by the number density, you get a different exponential in this case. So basically, in both cases, it's the heavier of the two particles that will set when this stops. So the exponential growth will stop when either of these states turns non-relativistic. Yeah, so the picture to have in mind is that this is unimportant initially. And then this rate per Hubble becomes order 1, and then you exponentially grow, and then you hit a mass threshold and stop the exponential growth at the correct time to hit the observed abundance. So and before the states would thermalize. So it's like a failed thermalization because you hit a mass threshold during the thermalization. Another way of thinking of this.
Does this require some coincidence? Because one temperature is determined by your interaction rate, and the other is your mass. the demise of.
Yeah, you're right. It does require a coincidence that the thing enters equilibrium like a few e-folds before one of these states turns non-relativistic. Yeah, so it needs a special choice of the size of the cross section given the masses. You're right. Okay. Thank you. Yeah, so this thing that gets exponentiated grows like 1 over temperature and then exponentially falls and can be order 1 for a period of time. And then you can have an initial amount of dark matter that exponentially grows and then flattens when the exponential growth factor is small. So that's the way this can be successful. Okay. So you can consider any mechanism for making the initial amount of dark matter, but this fits in nicely with freeze-in because there always will be some amount of freeze-in just as a consequence of the interaction that gives the exponential growth. Okay, so in the example, so you can use the interaction twice that gives the exponential growth, and that will give some freeze-in. So that will always be present in this model, some amount of freeze-in. And the assumption that psi is in equilibrium implies that there are other interactions that can be combined with the exponential growth to give freeze-in. So depending on where on the model now, either the top ones or the bottom ones can be more important. But there is some irreducible amount of freeze-in in this model, and that might be what sets the initial condition, or you could consider additional production beyond these. But the simplest case would be you freeze in initially from these types of processes, and then you exponentially grow to the observed amount. And in that sense, this would take freeze-in models where the couplings are too small to produce the observed amount of dark matter, and then bring the dark matter to the observed amount. So you could think of it as extending freeze-in to smaller coupling space.
So since this is exponential growth, could you get away with having, say, 1 particle of chi in our universe at reheating, say?
Yeah, that's a really interesting question. Actually, something that I've been thinking about. It's really hard, it turns out, to get to 1 per Hubble. Yeah, that would be interesting.
That would
because-
be the Cabrera monopole density.
Yeah, exactly. Yeah, and there may be lots, they'll find it. That could be interesting from the point of view of gravitational waves, because then you can get a very inhomogeneous exponential growth if you could have 1 per Hubble. So that was so with Michael Geller, we were thinking about that, and it turns out to be quite hard to get it to be that small, just because these freeze-ins typically give you a log per Hubble. Yeah, so I think that on the universe scale, this will be kind of a smooth transition of the exponential growth, but it would be really interesting to have 1 per Hubble. And from the point of view of the exponential, that would be fine. So you could exponentially grow 1 per Hubble to the observed amount. It's just given the irreducible freeze-in present in these models, it's actually hard to keep it that low. Yeah, so that's actually a really cool question. Okay. Yeah, so here's a toy model with both freeze-in and exponential growth, where the freeze-in is coming from this process, which, like I said, is generated to some degree. And then the exponential growth comes from this. So then the yield looks like this. You freeze in some amount, and then these are coupling sizes that would not produce enough dark matter from freeze-in, but then you exponentially grow up to the observed amount. You're only logarithmically, the size of the coupling you need is only logarithmically sensitive to the initial amount. And that's why these couplings are very similar here. So that from that point of view, you need a coincidence, or a more positive glass half full way of saying that is it's very predictive. That told you both ways, to be fair. Okay. Yeah, so this, for that point model, this shows the phase diagram. There's a bunch of ways you can get the right amount of dark matter actually with just these 2 interactions, but if they're big enough, it can be thermal. This thing that is giving the exponential growth, if it's actually in equilibrium, then that's been called semi-annihilations, like when you have 2 to 1, and technically that's actually similar to the WIMP, so then it would have to have a weak scale cross section. So that goes back to this old here by Francesco and Jesse. Yeah, so anyway, and here's like where the freeze-in is producing the observed amount of dark matter, and then there's a region at small coupling below the freeze-in coupling where the exponential growth can produce the observed amount of dark matter. So it's part of the phase space of these models and fits in with freeze-in in that from that perspective.
So out of curiosity, you have some region that's BBN excluded because the psi is less than half an MeV?
Yeah. Here we're taking the masses to give the observed amount of dark matter given these coupling sizes, and then we're assuming in this model that size in equilibrium with the standard model,
Mhm.
or had, yeah, so then you hit an ineffective bound.
But okay, so if you were to identify psi with a standard model particle, presumably
that'd be
you could maybe-
different.
You could maybe do it with neutrinos, right?
Yeah, and that's what I'm gonna do in the next part.
Okay.
Yeah, so that'll be the sterile neutrino application. That is, I think, the most interesting model we found with this. But yeah, here I'm assuming they're both non-standard model particles, but you're right that these constraints that are shown here are model dependent and you can get around them. Absolutely. Okay. Great. Here's the joke part. This slide is going to be like some fraction humor and some fraction serious, and you can decide which fraction. Really wish humor not on. Okay. Anyway, so yeah, so there in epidemiology, there's something called compartmental models where you group the population into what are called compartments, sick or not sick, or you could add a dead. So these are compartmental models, and the SIR model is the most famous kind of first example where that stands for susceptible, infected, and recovered. So those are the three compartments.
What is this? Sorry?
Susceptible.
Susceptible.
Susceptible, yeah, susceptible, yeah, so is in epidemiology, a susceptible person can be an infected person, and then you now have two infected come out, and then the amount of infected people or animals, whatever, mice, whatever it is, given by the solution to this differential equation. Yeah,
Where's the R?
Yeah, hold on. Okay, so anyway, here's our Boltzmann equation. So these equations are actually equivalent if you, with a certain mapping. Right, it's both exponential growth. Yeah, and so there's an exact duality between these equations. If you identify the infected compartment with the number density of chi, the susceptible number density of psi, the infection rate with the cross section. And here Hubble, interestingly, is playing the role of recovery. Because as the universe expands, like then this stops and then you all recover.
The dark matter is analogous to sick people.
Yeah, so
And if you allow for decays, you could also have dead people.
it would be interesting to extend this to other compartments. Models. There are extensions of SIR model where you add that compartment too. Okay, so this is the model that leads to the famous R factor, yeah, which is the number of people that an infected person infects on average per recovery time. That's how it's defined. So it's this ratio. And then so here, this is the answer here why the 3 by the way. So here, given this duality, then the analogous R is the thing that's exponentiated, right? It's the number of scatterings a dark matter particle participates in per Hubble time to make more dark matter. Okay. So this is exact duality. Okay. Is there any way I can pause Zoom?
No, it's just, normally we post these on YouTube afterwards. We don't have to if you don't want us to.
You can pause the recording in the middle.
Sure. Middle.
Sorry, you can mute it. You can also mute
Or
it.
some part of the
Sorry about the technical difficulties. Okay. So in our first paper, unfortunately, we didn't have a really good example, but so this is why we had to write 2 papers on this. We should have had this example initially in hindsight. But an application of this that I think is interesting is to sterile neutrinos, where the state that I called psi in equilibrium is an active neutrino. And the reason I think this is interesting is it's actually hard to get enough sterile neutrinos, and so that's it's a good candidate to consider exponentially growing. Yeah, so this shows a summary of current experimental status that was done for snowmass, and sterile neutrinos will be produced by oscillations from active neutrinos into sterile neutrinos, and this is famously called the Dodelson-Widrow mechanism. Just oscillations, and it works sort of this line here, and there's now, and it's basically all excluded from X-rays, or at least there's tension. Yeah, because you
For your 4-point interaction, 3 sterile and 1 active.
Yeah.
What's the size of that coupling?
Yeah, I'm gonna need a mediator to keep it infrared for the reason I said before.
Right,
So I'll show you examples in a second, maybe.
Okay.
Just wait.
all right.
Okay. So, yeah, the Donaldson-Woodrow, there's tension between that setting the neutrino abundance and experimental constraints, right? A stereo neutrino can decay to a photon and an active neutrino, and then you can see an X-ray line. So it's like a famous signal for this. And probably you should have seen it already. Colors come. Okay. There is a way of boosting the amount of stereo neutrinos that can successfully match the observed amount, called the Shih-Fuller mechanism. And here you assume, if you assume a large lepton asymmetry, then that changes the oscillations, kind of similar to MSW. You get corrections to you get a medium dependent correction to the mixing angle, and you can boost the stereo neutrino production, and this can successfully work. But you need a very large lepton asymmetry. It has to be 1 million or more times bigger than the baryon asymmetry for this mechanism to be successful, and that's possible, consistent with say BBM constraints on lepton asymmetry, which are pretty mild. But at high temperatures, failerons would normally set the baryon and lepton asymmetries to have a similar size. So for this to be successful, you need at low temperatures, after failerons have decoupled, a very ginormous lepton asymmetry has to be produced separately from the baryogenesis, and that's fine, but not simple. It requires infrared dynamics to produce this very large lepton asymmetry. That's sort of the favorite way of salvaging stereo neutrinos. So I'm going to argue our way is simpler if you include the complexity of whatever is needed to generate this in the model. Then I think ours will be similar, because we can just add one field to the minimal model. Okay. So getting towards Lintel's question of what are the couplings. So the model that we considered is, suppose there are sterile self interactions generated from a light mediator. So as a simple example, you could have a scalar that couples to sterols, and that generates sterile self interactions. And then that's the only ingredient you need to get exponential growth, because if you combine sterile self interactions with the mixing, that's part of the stereo neutrino model, then you generate.
And the mixing is caused by
There's Higgs insertion.
Yeah, it could be like a higher dimension operator, like.
Yeah,
Like
you
dimension
need
5.
another back computation.
Yeah, that's for any stereo neutrino.
Yeah.
Yes, you could take like the.
No, it's a standard.
Yeah.
Okay, fine.
Yeah, that's.
What is the
standard.
mixing value?
Well, yeah, I'll show you for us, but for Donaldson-Woodrow, sine squared 2 theta is up here. Let's see. Yeah, then we'll be able to extend that a bit lower. Okay, good. Yeah, so here's some example points, blah, blah, blah. I think I'll skip that. Okay. So here's the parameter space where this can work. So in this whole white area, we can get the observed dark matter abundance. So mixing angles far below the Donaldson-Woodrow mechanism that seems to be excluded by these X-ray searches. So this for us works over here. At light masses, we run into bounds from it being too warm. There's sort of 2 types: free streaming or the sort of dark BAO from this coupling. Yes, there's a dark sound horizon. Kind of here and here. But if you as you move to lower and lower mixing angle, you need larger and larger coupling for the process that gives the exponential growth. And at some point, just the dark matter self interactions become too big. So it's just ordinary dark matter self interaction, like 1 centimeter squared per gram bound. So this is a pretty big parameter space where this can have smaller mixing angle than what's excluded by X-rays, but successfully produce the observed by dark matter. So you can get a pretty big parameter space for stereo neutrinos that exponentially grow. So what's happening here is you produce initially some stereo neutrinos from ordinary Donaldson-Woodrow. You don't have enough to be the observed dark matter, but then they can scatter against active neutrinos, and you exponentially grow the stereo neutrinos to the observed energy density. So I would argue this is simpler than Shih-Fuller if you include the complexity needed to generate the very large lepton asymmetry. We're just adding to the minimal stereo neutrino one mediator and 1 interaction.
Although, I mean, people have played this game, putting the mediator on the active side.
Yeah, and that works too. I know, so I don't have a comparison, but yeah, people have. This is a little, this is less constrained, because there you have to worry about constraints on active neutrino self interactions. But absolutely, yeah, if you add additional interactions to active neutrinos, you change the matter effects, and you can also boost stereo production. That needs higher dimension operator, or is just gonna be marginal,
But yeah, the complementarity there is just that you don't have to worry about the dark matter self-interaction.
Yeah.
Now you have to worry about neutrino lab.
exactly. So I think that's interesting, and people have explored that. And unfortunately, I don't have a plot to show you the status, but yeah, there is, but that's another way of extending the minimal case.
Sorry, Jeff, your proposal is what is in this white area?
Yeah, the white area is,
EXTP?
yeah, we can work anywhere below Donaldson-Widrow in this plot. And then these green curves show the value we need of of this vertex to produce the observed amount of dark matter. And then the white area is where it's not excluded. Sorry, EXTP is some projected feature X-ray.
And
Yeah,
what
so-
is the relevance or how important it is to keep phi of the same order of MS?
Yeah, that's an interesting question. We just for simplicity chose it to have a mass nearby. If phi is heavier, then you can do the exponential growth when the temperature is of order of the phi mass. So the parameter space shrinks, but there is still parameter space there. We haven't fully explored how big that parameter space is, and it would be interesting to do. But yeah, but then it's like a UV dominated if you integrate out the phi. And that just means you need to do the exponential growth when temperature is on the order of the phi mass. And it should be after like the 100 MeV temperature when the Donaldson-Widrow is happening, if that's going to give you the initial abundance. But there's a pretty big gap between 100 MeV and the keV masses here, so you absolutely have some parameter space where the phi is a bit heavier, and we haven't fully explored that.
So in this computation, is sort of dependent sort of mixing angle on the temperature important, or can you just use vacuum mixing angle in this computation?
You cannot use vacuum mixing angle. It is important, but it's the same for us as the standard Donaldson-Widrow, so we were able to borrow from that literature to make this plot. But yeah,
So the thermal effect is important in this computation.
yeah,
I see.
yeah, they are important, very important. And yeah, and that Donaldson-Widrow is dominantly happening, if I remember correctly, when temperatures are around 100 MeV, and that's where you can think of it roughly as that's where the active neutrino medium mass is comparable to the keV scale of the sterile mass, and that's where the mixing is maximized. So it's very important to sure. In fact, yeah, the vacuum doesn't work.
I see.
And then in the Shih-Fuller, the medium effects change,
Yeah.
or when you add additional interactions. Yeah.
So the stereo neutrino mass is not set by the covering to the phi. Stereo neutrino has some other mass term.
Yeah. For us, yeah, there's just a sterile mass and a phi mass. Indeed, naturally, if you have a big hierarchy, then it would become tuned. That's what we're about.
No, just what's the contribution to the active neutrino mass?
Oh.
You have some mini seesaw going on here.
Right.
Yeah, that's small. Smaller than the active mass, yeah, for these mixing angles, yeah. Okay. But yeah, you're right, yeah, sorry, so you do a mini seesaw.
Is the region where you have Lyman alpha R sub S, is that just ineffective?
Yeah, we're doing something very crude, but it's where the here the dark interactions are important for the suppression in the matter power spectrum. Yeah, and then based on studies that have looked at that, you kind of get like dark acoustic oscillations and a suppressive structure. So then you can translate that roughly as some bound on the sound horizon scale in the dark sector, and then that was how we draw that curve. Yeah, so this is just ordinary free streaming, and then this is where the dark matter self interactions are important for this suppression in the matter power spectrum.
So if you plot the timeline of when the dark matter is produced, does the fact that you
Here's some example. These are 2 parameter points, and then here's like an example where you initially make it from Donaldson-Widrow, and the exponential growth is happening later.
Gotcha. Okay, so it's later.
Yeah, here because we chose the phi mass to be near the sterile mass, the exponential growth is happening at keV a few keV, or well, yeah, sort of close to keV temperatures. Which is why, yeah, that's around where the warm bounce matter anyway. Yeah, whereas Donaldson-Widrow is out at 100 MeV. Okay. Yeah, here the sterile and state and the phi are in equilibrium, so and there's some dark temperature. That you can think of that being produced that we're plotting here, so here the.
Dark matter mass for you is several keV. That's dark matter mass for you
Yeah.
is several keV.
Yeah, like 10 to 100 or, yeah, here's 100.
Is that red dot supposed to be where you are? Or?
Oh, these two red dots are just the example points
Yeah.
on the side. I skipped.
That's the
That shows
point you
the,
like. Right, so that's the. Usually red dot is the point you like.
it's the point that we chose. We chose to make this plot for.
Yeah.
I guess. If
That
I
is
dislike
that is the point that you like. Okay, so it's a-
Could you show it again, then? Is it
Yeah.
1 7.5?
Yeah, we chose one to be near the X-ray current
Yes,
bounds,
sir.
because
And
then
it's not warm. And that point.
yeah, you could argue about where to draw this curve.
Yeah.
So this might be warm. I think there are people who would say that this is too warm.
There's a little lukewarm.
Yeah, yeah, there are people who would say that that's too warm.
Uh-huh. Okay.
Yeah, and then people would argue, knowledgeable people, which I'm not one, would argue about where to draw this line, and there are some that are more aggressive, maybe. Yeah, this dashed line would be an example of a factor of 10 more aggressive in free streaming scale. I think there are people currently drawing lines close to that. Yeah, from Lyman alpha or like statistics of dwarf galaxies and it's a very interesting topic.
So, sorry, I got confused. The different colors of these dashed lines, what does it mean? So,
Well, yeah, we just took this to be excluded, and then this is kind of reach. Yeah, really, this is like a factor of 10 in free streaming scale from conservative constraints currently. So it's not really reach, but it just to give you a sense of where a factor of 10 in free streaming scale would enter on the plot.
so you expect that you will be able to reach that?
Maybe, yeah, I'm not an expert in these systematic center, these Lyman alpha bounds or things like the population statistics of dwarf galaxies, but people are. But like there are bounds sort of already being placed in this range. So that's sort of like a testable scenario. Yeah, indeed, for self interactions, I think this was like 1 and maybe this was like 0.1 centimeter squared per gram, I forget exactly, but. Yeah, so these are not really these are actually reached, these proposals, and then these are just kind of like
Guidance.
interesting region.
Since you have that diagram for scattering to produce two sterile neutrinos, would you ever be in a regime where you can just make the phi directly through inverse decays and then?
We are actually, well, I'm calling it this, but it's really that you're making it through inverse.
Okay.
Or yeah, so really there's an on-shell phi is what's dominating this process here. Yeah, and yeah, so that here, yeah, I skipped this, but I'm sure I'm showing various rates versus Hubble.
I see.
Yeah, and then this is the new S to phi, and then the one that is important here is new S alpha to phi. Yeah, so you get the exponential growth when this yeah, it's happening faster with Hubble. So yeah, actually in this case with a factor of 3 in mass, the phi's are on shell briefly. Yeah, good. Yeah.
Would this significantly affect the lifetime of the sterile neutrinos, having this interaction?
No, it doesn't affect the lifetime. Yeah, so you're just dominated by the lifetime is just coming from the normal mixing here. Yeah. Yeah, so yeah, so this makes it unstable and then it's just decaying like sterile to active photons.
But if the lifetime is very long.
Yeah. Yeah, I mean, these X-ray constraints are gonna, I forget, but something like 10 times the presentation universe. 10 to 10 times the presentation universe.
So here you use some scalar coupling, but since the relevant temperature is around the mass of the sterile neutrino, maybe just a myron type coupling those give similar prediction, I guess. If there's no suppression from derivative coupling. I guess.
You're wondering about scalar versus pseudo-scalar coupling?
Yeah. Maybe they give similar result.
That's an interesting question. Here we're assuming scalar. But yeah, I don't expect it to be different, but I'd have to think about it. Yeah. And you could also make a vector instead of a scalar, and that would be interesting to do too. We just chose a scalar coupling as a sort of quick example, but it would be interesting. to play with the different span of this and coupling here, that would be interesting.
So since this scattering is IR dominated, do you expect this to be more enhanced in the later universe? Because that goes like 1/T².
Yeah, until you hit the mass threshold, so once the photons are colder than a keV, then this exponentially shuts off. So.
Oh, I see. So you're not producing this
Yeah,
heavy.
actually, you can see that in this plot, that these all shut off. But yeah, so it's IR dominated in the sense that this sense, and then it shuts off, below keV. Okay, cool. So that's the first part. I was expecting it to be most of the time, but not quite that much of the time.
I think there are a lot of questions.
Yeah, you wanna go a bit over, that's fine.
You can go over a little bit.
Okay, I'll just keep talking and please stop me. Stop me at some point.
By 6 PM.
Yeah. Okay, I'm trying to think. I think at normal speed, this would maybe take 20 minutes, which would put me 10 minutes over,
Yeah, so maybe slightly faster.
slightly faster. Yeah, I don't really know how long it would take because this prior part was longer than I expected, so.
Yeah, you
realized-
Okay, stop.
If you stop thinking about it.
I'm just trying to filibuster myself. Okay, so take a breath though. It's good we take a breath because it's gonna be completely discontinuous from the prior part, which I could even just stop, but okay, I'm gonna now talk about oscillations between photons and dark photons, and the only similarity is that this very importantly is a non-equilibrium thing. Well, there were oscillations in the prior model too, but anyway, but otherwise unrelated. That people have thought a lot about oscillations between photons and dark photons. This is actually the leading constraint on a connectly mixed photon in part of the parameter space. The new thing that I wanted to highlight here that we looked at recently is these oscillations in the presence of millicharge particles in the early universe, and this can set a new constraint on millicharge particles or a new constraint on dark photons. They are related. The constraints are intertwined. So that's the new thing here. Okay, so very fast. Everybody knows all the experts here, so I can kind of skip this, but connectly mixed dark photon introduced by Bob. Hold on, I'd like to point to the citations to this paper. Because people actually didn't really care much about it for a long time and suddenly started caring a lot. Yeah, I was worried that we might have hit peak dark photon 2019, but because there was a 2-year lull from, I think that's the pandemic, because then we're now past that, so it's still growing.
Okay, what are the peaks, the 2013?
Oh, these are just times I thought were interesting. Yeah, I don't know. I mean, like this would be like Pamela and Attic.
Oh, that was the Pamela.
Yeah, this is kind of like when the first LHC results are really settled in to our minds. I don't know, but I don't know. The sociology is interesting, but it seems to still be growing. So what I'd say, the takeaway from the slide is if you're not working on dark photons now, you will be soon. So you should pay attention.
Exponential growth.
Yeah. Okay. So one phenomenon that this can give is oscillations between photons and dark photons. The dark, you're in the small coupling limit where the dark photons are not in equilibrium and they can be produced from photons through oscillations. These oscillations are negligible in vacuum, so medium effects are very important here, and they go through resonance if there's a mass matching. So like if the dark photon mass matches the plasma mass of the ordinary photon, you can have resonant oscillations that can affect the CMB and be observable, and it's interesting. You can have photon just can disappear. This is what I'm going to focus on. If there are dark photons present in the early universe, you can also inject photons. That's interesting too, from the point of view of things like radio observations and 21 centimeter measurements. I'm not going to talk about those now, but you can ask me later. So very importantly here is the evolution of the photon's plasma mass. This shows how it evolves with redshift. It just depends on the free electron number density, so it's sensitive to the expansion of the universe and recombination and reionization. And then if the dark photon has some mass, like a bare mass, then you can get a level crossing at a certain redshift. So it might sound fine-tuned saying the mass is equal, but because the photon's plasma mass scans many orders of magnitude, if there is a dark photon with mass anywhere in this rather large interval, then you'll get level crossings at some point. And for this example shown in the plot, you actually get level crossings 3 times. And each of those times you can produce large amounts, but then you get migration from whichever number density is bigger into whichever one is smaller.
So the peak at later times, that's reionization.
Yeah, yeah, this is reionization. Yeah, and this band is some like Planck uncertainty, some Tanch model, but yeah. Yeah, exactly. So this is recombination is where it's steeper suddenly, and then reionization gives you just non-monatomic behavior. Okay, so you can compute the radius oscillations using something called Landau's Zener formula, which is something in quantum mechanics. When two energy levels cross, then you can have resonant movement between the two states. This has been applied to neutrino oscillations before, and the same formalism was adapted to photon-dark photon oscillations. First in 2009 in this paper. And the effective resonance here is really big. So here this plot shows the oscillation probability per epsilon squared. So this is basically, you can think of this as the amount of enhancement relative to vacuum mixing, and it's a factor of 1 billion or so. Because this Landau Zener has a 1 over time. Yeah, so you have the entire universe to oscillate. It's a sort of Hubble size that enters this enhancement. The amount of time the universe sits on resonance will be related to Hubble. Okay.
These guys were young when they.
Yeah.
Okay,
Let's not distract Josh.
Well, you
I'm not gonna abuse this.
Don't worry about people who never worked on that program.
But as I said, you will. That was the whole point.
Well,
Back here, you will work on dark photons, Carlos.
I posted a paper today that
There you go.
has some mixing.
There you go. Oh, see that
Shame on me.
the exponential is predictive. Okay, sorry. This is worth a minute. Okay. So the oscillations of ordinary photons to dark photons is the dominant constraint on dark photons in this part of the epsilon F plane. So this is just distortion to the CMB. You lose some of the CMB, it just disappears suddenly. And now it's not a black body anymore. This is a 1 over energy in the oscillation probability. So you convolve the CMB with some 1 over energy dilution. Yeah, okay. So now I want to explain how Miller charge can be related to this, but first let me just say dark photons are special because they decouple at low masses. That's why there's this huge parameter space where stars are not killing you, and that's actually unique for light particles with normally are produced in stars with huge amounts. So like a light scalar or something can't have a coupling of 10⁻⁶ to the standard model if its temperature, if its mass is way below temperature of stars. So dark photons are actually special because massless dark photons decouple, and that allows for very large couplings to the standard model. Yeah, they decouple, well, just technically you can see that here. If there's no mass for the dark photon, then you can redefine it to remove the kinetic mixing. And then you can think of it basically as just define the linear combination of couples electromagnetic current as the photon and the orthogonal linear combination decouples in the massless limit. And then in practice, that always means that any experimental probe has some mass over energy scale decoupling. So they decouple from stars and from laboratory probes at very small masses. So dark photons are special.
So in the plot with all the constraints on it, there's always that region that says you can be dark matter above all of that, but like I could produce this through inflation and put it anywhere in the white space, couldn't I?
Oh, yeah, you're asking about this?
Yeah.
This is an experimental constraint. If it's all of dark matter, then it injects energy from oscillations into ordinary photons.
I see, okay.
And then yes, if it's all of dark matter, there's a stronger bound that's given by this green curve.
Okay.
And then these bounds apply if it's not the dark matter. But yeah, you're right. Inflation can put it wherever, but actually then you're excluded here.
Gotcha.
Yeah, like by reionization or something. Okay, so the massless dark photons do not couple if there is a dark current, and that's where Miller charge particles can be interesting. They can let you probe exactly massless dark photons. If you have a dark current, if you make the same redefinition where you define the photon to a couple of electromagnetic current, then well now the dark photon is coupled to the dark current, so it's still present. And a dark current is equivalent to Miller charge particles after this change of basis. So as the photon picks up an epsilon coupling to any dark current. That's actually the nicest way of explaining of generating Miller charge, starting from keeping charge quantization initially, then add kinetic mixing. Okay, so massless, summarizing the last two slides, massless dark photons exactly decouple if there's no dark current, but if there is a dark current, then they don't decouple, and then you have mill charge particles.
Just to be clear on the notation,
Oh,
I
yeah.
assume that the gamma mu at the bottom is a Dirac matrix, but the gamma mu in the middle is not.
No, they're all photons.
Okay, so the last one, the
This
last.
is the Dirac.
That's a Dirac matrix.
This is Dirac.
The light above that.
This is Dirac, and then everywhere else it's a photon.
Okay,
Yeah,
just-
I apologize.
okay, no worries.
What are you gonna do? Okay, so
Yeah, gamma D is not a mutation.
2 minutes. I think we can even finish the time lapse. Yeah, I apologize. Okay. But only a little bit. Okay. So if you have millicharged particles, then they change the evolution of the plasma mass of the dark photon. And that, yes, this shows examples where there's either relativistic or non-relativistic millicharged particles. Before I was assuming just a bare mass and no millicharged particles, but if there's millicharged particles present, you can get trajectories like that, and it changes these level crossings. So that's the case we looked at in this recent paper. Yeah, now the oscillation probability actually depends on both masses, but anyway. So this lets you probe exactly massless dark photons, which are normally untestable, if there's millicharged particles present in the early universe. This shows, yeah, the constraint from CMB distortions for the x-axis is the redshift 0, the present value in our universe of the dark photon's mass. Okay, so I'm going to just end by showing you the punchline. So we can set a new bound on millicharged particles just by, if we assume there exists a massless dark photon, which is theoretically, I think, the nicest motivation for millicharge in the first place. So this shows millicharged particle mass versus coupling, and then the constraint you can currently set from the CMB, from photons disappearing to dark photons, and then future unfunded, I think these have changed names, but anyway, there are proposals for experiments that could measure CMB much more precisely. Then there's less measured in the fire component of the COBE satellite anyway, then that would be quite interesting and test new parts of the millicharge parameter space. Okay. Yeah, and this, if you have some dark radiation that composed of millicharged particles, and you assume there exists a massless dark photon, then you can test it again by the CMB. So this just shows it in this sort of ineffective as a variable, and you're getting, yeah, it's a much smaller ineffectives, of course, than like direct ineffective constraints. Okay. 1 minute over. That was kind of fast, but I did finish. Okay, so that was a 10-minute segment of the talk. Just to advertise that you can that oscillations from photons into dark photons, which distort the CMB, and we've studied them in the presence of millicharged particles. This allows for the first time to test exactly massless dark photons. And then most of the talk, though, was something different. It was about exponential growth of dark matter, which is a new idea for how dark matter could have been produced that's different from thermal, relic, or Friesen. And an interesting application is it opens up new parameter space for stereoneutrino dark matter. But it's a general idea, and I'm sure there are other models that maybe are cooler, so it'd be worth thinking more about that. Thanks.
Josh, we had lots of questions during the talk, but are there any maybe quick-ish questions? Still.
So for the resonance production during the mass crossing, you said you used basically the Hubble time as the time you get this resonance. So
Yeah.
the question is.
Yeah, exactly. Because Landau's Zener formula has a time derivative in it. Yeah, yeah.
And my question is, does that require all of the dark photons inside your Hubble patch has the same phase when they oscillate? So it's like if they are coherent wave-like during this process, and is that a condition for this to happen?
That's a good question, Shane.
I'm not sure he's considering a classical background coming up. You just
Let's
said-
not. I'm in the particle limit.
Yeah, so what you're saying is if there's a classical background of that, I don't think he's.
Yeah, I'm not,
He's considering just back
yeah,
photon as a.
that is like an issue maybe for these constraints here, but that's not.
As a particles. I think.
Yeah, but you're right, I'm in the particle limit.
Okay, so this, I should think of this as,
These are just particles.
Yeah, like neutrino oscillations.
let's see.
Just to make sure your signal for Milli charge is that they will radiate our photon. Instead,
The signal is that the CMB black body is distorted because photons are oscillating into dark photons and you lose some of the CMB.
and then this will be different.
Yeah, if there's
From the case where you just have a tiny hypercharge.
yeah. Yeah,
Because of the dark photon plasma mass.
yeah,
Well, there's no dark photon.
if there's no dark photon, the signal doesn't exist, so.
But you do still have a Milli charge part.
Yeah, indeed. But here the experimental signal is photon disappearing. So this is telling apart those two types of mill charge from that point of view.
So some kind of a CMB distortion.
Exactly.
But you had some requirement on the fractional abundance of millicharge particles, right? Can you remind me how sensitive it is to that?
Yeah, it is, well, like, yeah, the sound effective plot is, then it's the y-axis, so that's.
But for the other plot?
Yeah, here it's dark matter, like, yeah, in our paper, we have some plots. Yeah, this is kind of the most optimistic case is the maximal amount. Yeah, so we have plots with 3 smaller values that I could show you after, but it is sensitive to it. And the parameter space that you're testing is smaller if you have less of it. Yeah,
Thanks.
Great, if no further questions, let's thank Josh again.
I think the interpretation for the 2013 peak is that everybody